Geologists are confident that plate tectonics has operated over the last 2 billion years, and perhaps even longer. The question that arises is, what came before Pangaea, and what does the future hold? Pangaea was the most recent, but not the only supercontinent to exist in the geologic past. We can get some idea of what came before Pangaea by taking a closer look at the fate of this supercontinent. Recall that Pangaea began to break up about 165 million years ago, and the pieces are still dispersing today. Crustal fragments from the breakup of Pangaea have already begun to reassemble to form a new supercontinent, as evidenced by the collision of India with Asia. The idea that rifting and dispersal of one supercontinent is followed by a long period during which the fragments are gradually reassembled into a new supercontinent having a different configuration is called the supercontinent cycle. We will look at the formation and eventual breakup of Pangaea as one episode in the supercontinent cycle. The plate motions that resulted in the breakup and dispersal of Pangaea are well documented. The dates when individual crustal fragments rifted from each other and their subsequent movements can be computed from the geomagnetic stripes left on the newly formed ocean floor. However, this technique cannot be used for reconstructing events prior to the breakup of Pangaea, because the ocean crust from this time period has been subducted. Nevertheless, using ancient geologic structures and apparent polar wandering paths, the general trends of plate movements can be established. The formation of Pangaea is thought to have begun between 700 and 550 million years ago with the breakup of an earlier supercontinent. The reconstruction of this supercontinent is still being debated. Fragmentation of this pre-Pangaea supercontinent produced a landmass located in the southern hemisphere that came to be called Gondwana. This large continent was comprised mainly of present-day South America, Africa, India, Australia, and Antarctica. 3 smaller fragments also resulted: North America, Siberia, and northwestern Europe. This is another view of the distribution of the continents 510 million years ago. Later, a small fragment called Avalonia was rifted from Gondwana. The continents of North America, Siberia, Northern Europe, and Avalonia began to collide about 430 million years ago, forming a landmass that straddled the equator, while the southern continent of Gondwana remained centered over the South Pole. Pangaea began to take form over the next 100 million years, as Gondwana migrated northward and collided with North America and Northern Europe. As the developing supercontinent drifted northward, smaller fragments were added to Eurasia, and South America rammed into North America. By 230 million years ago, the supercontinent of Pangaea was nearly complete. Several crustal blocks, which today make up much of Southeast Asia, were never part of Pangaea. Even before the last crustal fragments were added to Pangaea, North America and Africa began to rift apart, This event occurred some 165 million years ago and marks the beginning of the breakup and dispersal of this newly formed supercontinent. Rifting that formed the South Atlantic began about 130 million years ago near the tips of what are now Africa and South America. As the Atlantic Ocean continued to grow in size, crustal fragments were being added to Asia. Between 90 and 50 million years ago, Australia separated from Antarctica, while India continued on its collision course with Eurasia. Thus, the fragmentation of Pangaea overlapped in time the initial phase in the assembly of a new supercontinent. Beginning 50 million years ago, India collided with Asia to produce the Himalaya Mountains, while Africa and Australia continued their northern migration. During the last 20 million years of Earth history, Arabia rifted from Africa to form the Red Sea, and Baja California separated from Mexico to form the Gulf of California. Meanwhile, the Panama Arc joined North America to South America to produce our globe's familiar modern appearance. Although present-day continents appear to be stationary, they are drifting around the globe much like pre-existing continents have done for the past several hundred million years. Click on the controls to view the movements of crustal blocks from 200 million years ago to the present. A third type of plate boundary is called a transform fault. Transform faults occur where plates slide horizontally past one another, without generating new lithosphere as occurs along divergent plate boundaries. And without the destruction of lithosphere as occurs along convergent zones. Transform faults join the globe's active belts into a continuous network. Most transform faults join two segments of the oceanic ridge system. Here, seafloor produced at one ridge axis moves in the opposite direction as seafloor produced at an opposing ridge segment. The adjacent slabs of oceanic crust grind past one another, sporadically generating earthquakes. Transform fault boundaries can also join divergent plate boundaries where new crust is being created with convergent plate boundaries where crust is being destroyed. For example, along the western margin of North America, the Mendocino Fault connects the Juan de Fuca Ridge with the Cascadia subduction zone. Here, the fault facilitates the movement of seafloor generated at the Juan de Fuca Ridge to its site of destruction beneath North America. Although most transform faults are associated with oceanic ridges, some, like the San Andreas Fault in California, cut through continental crust. Such situations provide geologists with an opportunity to study transform faults firsthand. Along the San Andreas Fault, the Pacific Plate is moving toward the northwest, past the North American Plate. Evidence for this movement is provided by offset stream channels. Sporadic slippage along the fault over hundreds of years produces an offset stream channel. If movement along the San Andreas Fault continues along its current path, that part of California west of the fault will become an island off the west coast. Perhaps millions of years into the future, this island will collide with Alaska. A more immediate concern is the earthquake activity triggered by movements along this fault system. Although new lithosphere is continually being produced at divergent plate boundaries, the surface area of our planet is not growing larger. To balance the amount of newly created lithosphere, older portions of oceanic lithosphere descend into the mantle along convergent plate boundaries. Convergent plate margins occur where two plates are moving toward each other and the motion is accommodated by one plate sliding beneath the other. Convergent plate boundaries are also called subduction zones because they are sites where lithosphere is descending into the asthenosphere. Deep ocean trenches develop between two converging plates and indicate where the subducting plate begins its descent beneath the overriding plate. Subduction occurs because the density of the subducting lithospheric plate is greater than that of the underlying asthenosphere. Older oceanic lithosphere is cooler and denser than the underlying asthenosphere. By contrast, continental lithosphere is less dense and therefore more buoyant, which prevents it from being subducted to any great depth. As a consequence, the subducted plate is almost always oceanic. Some slabs of oceanic lithosphere descend into the asthenosphere at angles of only a few degrees, whereas others plunge nearly vertically. The angle at which oceanic lithosphere descends into the asthenosphere depends on its density. When a slab of lithosphere is less than 10 million years old, it is typically less dense than the underlying asthenosphere and subduction is nearly horizontal. As oceanic lithosphere ages, it cools. This causes it to thicken and increase in density. Once the age of oceanic lithosphere exceeds 10 million years, it is more dense than the asthenosphere and will sink given the opportunity. In parts of the western Pacific, some oceanic lithosphere is older than 160 million years. This is the thickest and most dense in today's oceans. The subducting slabs in this region typically descend into the mantle at angles approaching 90 degrees. It is important to realize that a subducting plate does not follow a fixed path into the mantle. Rather, it sinks vertically as it descends, causing the trench to retreat or roll back. As the subducting plate sinks, it creates a flow in the asthenosphere that pulls the overriding plate toward the retreating trench. Although all convergent plate boundaries have many similar characteristics, they are highly variable features. Nevertheless, they can be placed into one of three broad groups based on the type of crustal material involved. Convergent plate boundaries form where continental lithosphere overrides oceanic lithosphere, where one slab of oceanic lithosphere is subducted beneath another, or where two blocks of continental lithosphere converge and eventually collide. Let's take a look at what happens when an oceanic slab converges with continental lithosphere. Whenever a plate capped with continental crust converges with a slab of oceanic lithosphere, the buoyant continental block remains floating while the denser oceanic slab descends into the mantle. When the descending oceanic slab reaches a depth of roughly 100 kilometers, melting is triggered within the wedge of hot asthenosphere that lies above it. But how does the subduction of a cool slab of oceanic lithosphere cause mantle rock to melt? The answer lies in the fact that water acts like salt does to melt ice. That is, wet rock in a high-temperature environment melts at a lower temperature than dry rock. Sediments and oceanic crust contain a large amount of water which is carried to great depths by a subducting plate. As the plate plunges downward, water is squeezed from pore spaces as confining pressure increases. At greater depths, heat and pressure drive water from hydrated minerals such as amphiboles. At a depth of roughly 100 kilometers, the asthenosphere is sufficiently hot that the introduction of water typically leads to partial melting. The semi-molten rock generated by this process contains as little as 10% melt, which is intermixed with the unmelted mantle rock. Being less dense than the surrounding mantle, this hot, mobile mixture gradually rises toward the surface as teardrop-shaped structures. When this partially molten material reaches the base of the crust, it is thought to pond beneath the somewhat less dense continental rocks. Here, fluid basaltic magma separates from the unmelted components and continues its ascent. Depending on the environment, mantle-derived basaltic magma may rise through the crust to feed volcanic eruptions at the surface. In a continental setting, however, basaltic magma typically melts and assimilates some of the crustal rocks through which it ascends. The result is the formation of silica-rich magmas having an andesitic composition, or less often, a rhyolitic composition. On occasions when andesitic magmas reach the surface, they often erupt explosively, generating large columns of volcanic ash, pumice, and gases. A classic example of such an eruption was the 1980 eruption of Mount St. Helens. The volcanoes of the towering Andes are the products of magma generated by the subduction of the oceanic Nazca Plate beneath the South American continent. This chain of volcanic peaks, termed a continental volcanic arc, identifies the region of intrusive and extrusive igneous activity associated with an oceanic continental convergent boundary. Another active continental volcanic arc is located in the western United States. The Cascade Range of Washington, Oregon, and California consists of several well-known volcanic mountains, including Mount Rainier, Mount Hood, Mount Shasta, and Mount St. Helens. Here are 3 recently active volcanoes in the Cascade Range in Washington State. Rotate by dragging to view these volcanoes from different angles. Rotate these before and after diagrams to show the transformation of Mount St. Helens caused by the May 18, 1980 eruption. Now let's look at what happens when two plates composed of oceanic lithosphere converge. In this setting, one oceanic slab descends beneath the other, often initiating volcanic activity at the surface. Here, volcanoes grow up from the ocean floor rather than on a continent. Should the volcanoes continue to grow, they will eventually reach the surface to form a volcanic island arc, or simply an island arc. This image shows a volcanic island arc that is part of Indonesia. Most volcanic island arcs are located in the western Pacific, where they form parallel to a deep oceanic trench. Examples include the volcanic island arcs of Japan, the Aleutian Islands, the Tonga Islands, and the Philippines. Only two volcanic island arcs are located in the Atlantic: the Lesser Antilles Arc adjacent to the Caribbean Sea, and the South Sandwich Islands in the South Atlantic. A third type of convergent plate boundary exists where two lithospheric plates, each carrying continental crust, collide. As you saw earlier, when an oceanic plate is subducted beneath continental lithosphere, a volcanic arc develops on the continent. Because continental crust is too buoyant to undergo appreciable subduction, a collision between the continental fragments results. Such a collision occurred when India rammed into Asia and produced the Himalayas, the most spectacular mountain range on Earth. The formation of the Himalayas began about 150 million years ago when India separated from the supercontinent of Pangaea and began to slowly drift northward. About 45 million years ago, India reached the trench that was located along the southern margin of Asia. The continued northward migration of India deformed and elevated the margins of these continental blocks. Gradually, these lithospheric plates were shortened and thickened, producing the spectacular Himalaya Mountains and the Tibetan Plateau. Other examples of mountains formed by the collision of large continental blocks are the Urals, Alps, Caledonians, Pyrenees, Caucasus, and Appalachians. At divergent plate boundaries, plates move apart. Most divergent plate boundaries are located along crests of oceanic ridges. Let's examine the Mid-Atlantic Ridge, which extends along a north-south path down the center of the Atlantic Ocean. Here, as the plates move apart, the gap is filled with molten rock that oozes up from the hot mantle below. Gradually, this molten rock, called magma, cools to make new slivers of sea floor. In a continuous manner, spreading and upwelling of magma add oceanic lithosphere to the edges of the diverging plates. This mechanism has created the floor of the Atlantic Ocean during the past 160 million years and is called seafloor spreading. Average rates of seafloor spreading are about 5 centimeters per year. Some of the slowest spreading rates occur along the mid-Atlantic ridge, whereas rates exceeding 15 centimeters per year have been recorded along the East Pacific Rise. Although these rates of seafloor spreading seem slow on a human time scale, they are rapid enough to have generated all of Earth's ocean basins in the last 200 million years. Spreading centers can also develop within a continent, in which case the landmass may split into two or more smaller continents. This is known as continental rifting. Continental rifting takes place where forces pull the plate in opposite directions. As the lithosphere stretches, molten rock rises from below to upwarp the crust. Eventually, the crust fractures to form a long trough called a rift valley. Slowly, the rift valley lengthens and deepens. The East African rift valleys are examples of such features. If spreading continues, it will extend to the plate margin and split the landmass in two. Much like South America and Africa did over 100 million years ago. At this point, the Rift Valley becomes a long, narrow sea with an outlet to the ocean, similar to the Red Sea. Consequently, the Red Sea provides Earth scientists with a view of how the Atlantic Ocean may have looked in its infancy. Continued divergence brings us back full circle to the development of a spreading center such as the present-day Mid-Atlantic Ridge.